All right, so we've been building up to this across the past couple of videos. We're going to talk about the arc length of a parametrically defined curve. And I think this is actually a really powerful tool. And it was only as I was sort of making this that I realized that, yeah, this has a lot of benefits over the previous video we spoke about where we determine the arc length of a curve that's defined in Cartesian coordinates or is defined using y as a function of x. Anyway, we'll get to that in a moment. So let's really break this down. Remember, to parametrically define something is we say that the coordinates of some point in space are defined as functions of some other parameter. So we call that parameter t. So if we have the point x is a function of t itself, and the point y is a function of t as well. So we can call that g of t. We can call x f of t, right? Now, to make things extra confusing, we've changed the notation a bit here. In previous videos, we just called x of t the x coordinate, but now we're just going to introduce this f of t, and hopefully you'll see why we need to do that. So we've got x and y being f of t and g of t. Okay, in two previous videos, we spoke about the following key results. The first one is this, which is the derivative of a parametric equation. So dy dx is equal to dy dt over dx dt. And so for the same reason as in the previous video, we're just going to call dy dt, well, that's just g dash of t. And dx dt is just f dash of t. We've just sort of changed the notation a little bit because otherwise later on we're going to get fractions upon fractions upon fractions. And this is just a little bit easier. So hopefully that is not surprising to you. If it is, definitely go watch that previous video. One of the other results we came up with is that the arc length on a curve that's defined as a function of x is equal to the integral from a to b of the square root of 1 plus the derivative of y with respect to x squared dx. So again, if that's surprising, definitely go back and watch the video about this. But what we can do now is we can actually take our understanding a little bit further because now we're talking about parametrically defined curves. So hopefully immediately we could say, we're going to take this piece of information, right? But we're no longer integrating between A and B. We're integrating between values of T. So we're going to call that T1 and T2. So literally just taking this and changing A and B to be T1 and T2. And I'll show you why we're allowed to do that in a moment. Okay, then we're going to take the square root of 1 plus g dash of t. Remember, dy dx is g dash of t on f dash of t. So we're just replacing dy dx with g dash of t on f dash of t, and we have to square it. Then we're taking the integral with respect to x, so dx at the end on the outside. Okay, what we could do is we could change this dx. So let me explain. We know that dx dt, the denominator here, is just equal to f dash of t. So if we rearrange this for dx, we're going to get that dx equals f dash of t dt. And so with that information, what we can do is we can replace this dx with f dash of t dt. So with all I've done here is with the dx, we've just put f dash of t dt. Okay, and now we're almost actually there, which is exciting. So what we can do now is, and this is where it's a bit tricky, but if we were to bring this f dash of t into the square root, well, if we squared it and then put it inside the square root of something squared is just itself, right? So we get f dash of t squared sort of sitting out the front, multiplied by 1 plus g dash of t on f dash of t all squared. And then we're just left with dt on the outside, right? dt. Okay, expanding that f dash of t squared into the brackets, we get f dash of t squared. So multiply that by that, gives us f dash of t squared. Okay, plus, all right, f dash of t squared multiplied by g dash of t on f dash of t squared. The f dashes of t cancel out, so you're just left with g dash of t dt. All right, and now as our final conclusion, right, we can say this, and this is just another way. These two things are equivalent, right? F dash of t is dx dt. And we had that here, right? F dash of t is dx dt. So I've just replaced f dash of t with dx dt. Just changing the notation. Same. We haven't really done anything from this step to this step. G dash of t, well, g dash of t is dy dt. right? So we get this as our conclusion for the arc length of a parametric curve. And what I've been realizing as I've made this video, and I'm keen to see what you think, is the following. So let's just jump over here to sort of get a feel for it. I've realized that this is a much more powerful tool because if we define some curve in terms of t, we might get something like this. Now this is not a function, as you can see, because it would fail the vertical line test. So it's not a function, but what this allows us to do is still able to find the arc length of it. And let me explain in more detail. So obviously this point A is f of t, g of t. And this is sort of the path that it would trace out between t1. You can see t is 0.1 here, and it goes to a maximum of t being 1. Okay, but that's a more powerful tool, and hopefully you can see why, because if we had it as a function between A and B, well, A and B might be here and here, but it's also down here and down here, A and B. Those X values, A and X value B, sort of line up, in multiple positions. So like there and there, and then there and there. So then it's like, well, how do we find the arc length then for something that's not a function? And then so this is, I think, why we learn this is because we can find the arc length of something that looks like this. And when we are doing parametric curves, we do get these cool, funky looking relations a lot of the time. They're not functions. And so we still need a way to find the arc length of those relations. And yeah, that's what we get. We get this as our result. So that's why I think it's a pretty cool result because it's a more powerful tool than this, right? Although this is also important. Let me know what you think. That's just what I thought about it. Let me know if you have any questions and good luck with all your studies. I will see you soon.